dear students. I am your chemistry teacher. I am Vaishnavi Dubey. And yeah, see, today I am starting with one of the very important topic of our physical chemistry, and that is equilibrium. All of you must be aware of the importance of this topic. See, this topic is important itself, and it is also important because it comes in the combination of other four other chapters also, like solutions, like chemical kinetics, like thermodynamics, redox, and sometimes electrochemistry also. Lot of the other concepts are also mixed together, and they are asked over here in the equilibrium. Okay. Now, starting with the simple definition of equilibrium. Equilibrium word has similar word like equal something. Okay. So with this equal thing, there is this one simplest definition that you can learn, most applicable definition that I will give you. It is the point of reaction where rate of forward reaction becomes equal to rate of backward reaction. Okay, this is the most applicable definition of equilibrium that you will ever get, right? Okay, now let us understand this. What is actually the rate of forward? What is actually the rate of backward reaction? When the amount of reactant that is being formed and the amount of product that is being formed has become equal, such that it is visible as the reaction is not occurring at all, right? The forward and the backward is similar. Representing it through the graph so that we understand it even more. See, the graph is, suppose I am drawing this graph of concentration with the progress of reaction or time of the reaction, right? So, if suppose we are taking this reaction from reactant to product, this is what is happening. So, product concentration is increasing and the reactant concentration is decreasing, like this. This is the graph that I have drawn. Okay, one hypothetical graph. In this graph, if you see this point of intersection, usually students think it as the equilibrium reaction, equilibrium point. But this point is the point where the reactant and product concentration is there, not where the equilibrium has reached. Equilibrium is not when the reactant and product is equal. No, not always. Equilibrium is when the amount of reactant and the amount of product formed is equal, is same, constant. The concentration and product, the reactant and the product concentration becomes same. Okay, constant. And that has become over here. This is the point where the reactant and the product concentration have become same. So this is the equilibrium point that we have reached. Okay, telling you through another graphical representation. See, same concentration and progress of reaction. First, suppose the product concentration is increasing and reactant concentration is decreasing. It is this way, right? This is the graph. Now, if you see in this graph, what is happening? This graph is not intersecting. The graph is not intersecting, but there is equilibrium when the reactant and product concentration has become similar. Okay, this is what the equilibrium is over here. Now, what is the difference between these two then? Right? Now, if you see this as from 0 to some reaction, this happening, right? To this reaction, this is the half of the reaction. Okay? This is the half of the reaction where reactant has become equal to product, right? This is the half of the reaction, which the reaction have crossed to come to equilibrium. So somewhere here equilibrium has been reached. Somewhere here equilibrium has been reached. Okay. Now, if you see here, suppose this is 0 to this reaction, then how will the reaction have not reached? The reactant and product concentration have never become equal. They have not intersected. So half of the reaction has not reached, but the equilibrium has reached. So equilibrium have reached over here. That means they both have represented that this equilibrium is reached in this towards the end of the reaction, right? Towards the end of the reaction. But here, towards the start of the reaction, the equilibrium has been achieved. Okay. Now, third thing, if I represent over here, that is with the same progress of reaction and the concentration. This is the product that is increasing, and the increase is same as the reactant decrease. This is the graph where these lines are coalescing. This is the same line, right? Same line. That is, this line is representing equilibrium also, and this line is representing the reactant and product concentration to be equal also, right? So this is representing that from here to some reaction, half of the reaction is also done, and this is the only point of equilibrium, right? So from here, what I want to tell you is equilibrium can be attained from both the sides, and equilibrium can be attained at the half of the reaction, in the beginning or at the end. So from here, from the definition, we see that equilibrium is not a reaction; it is the point of the reaction. It is the point of time of the reaction, where this rate has become equal to the forward, equal to the backward rate. Okay, now representing the graph like this. Rate for suppose, instead of concentration, I am representing as a rate with the progress of reaction. And if I draw the first type of a graph like this only, here, like this, right? Now here it represents the rate is equal and this rate is also same. The rate has become constant, but the rate has not become equal at the end. So rate should be equal for equilibrium. Rate has become equal over here. This is the rate where rate of forward is equal to rate of backward. So this is the equilibrium that we have reached. You understand? Through the graph, the differences. Okay. Similarly, if I make this graph with the rate and the progress of reaction, and the graph is like this, for suppose, then at this graph, it has never attained equal rate of forward and backward because the graph is not intersecting. So here, at this place, there is no equilibrium. For this graph, equilibrium has not been attained, equilibrium is not defined. Right? Next, if you see here, the third type of a graph, the graph having a same line like this. Then this is the point of equilibrium. It is very clear. Now it has become very easy to see over here. Right? Now, if you see, we have three types of equilibrium. Right? We have three types of equilibrium. We have physical equilibrium, then we have chemical equilibrium, and then finally we have got the ionic equilibrium. Okay. For the physical equilibrium, it is the physical states that we have to see. Physical state that we have to see, and that will be from gaseous to liquid, and from liquid to solid, or from solid to gaseous equilibrium that we have to see. Okay. So, in the physical equilibrium, it is only the physical states that are involved, that the rate of sublimation is equal to the rate of crystallization, or the rate of evaporation has become equal to the rate of fusion, right? So that way. Next is the chemical equilibrium that we have to carry right now. Chemical equilibrium, I will consider, first of all, I will consider one chemical equation, and that will be A plus B is in equilibrium with C plus D. A, B, C, and D. I'm saying this is a balanced chemical equation. Okay, now with this, I have to calculate the rate of reactions. Now, with the rate of reaction, I have a rate law expression that is taught in the chemical kinetics chapter. And the rate law expression says that rate of a reaction is directly proportional to the concentration of reactant to the power of their stoichiometric factor. Okay? This way. So applying it over here, this is the rate of forward reaction, this is the rate of backward reaction. So for rate of forward reaction, it is the concentration of, proportional to the concentration of A, proportional to the concentration of B, like this. Right? If I remove the proportionality sign, it will be the equilibrium constant A. For the forward reaction, F, A, and B as it is. Similarly, writing for the backward reaction. Now see, for the backward reaction, the reactants become C and D. Right? So it will be C and D. Right? For equilibrium to happen, rate of forward should be equal to rate of backward. Rate of forward equal to rate of backward, that means Kf, A, B will be equal to Kb, C, D. Like this picture. Okay? So rearranging Kf upon Kb will be equal to C. That means product concentration upon the reactant concentration raised to the power of the stoichiometric coefficient. This is called as the equilibrium constant. This is very important. This is called as the equilibrium constant for the concentration studies with respect to the concentration, because we are calculating with respect to concentrations. Okay. Important point about this is this Kc we are calculating with the help of concentration, but it is independent of concentration, right? It is independent of concentration. Kc is independent of concentration, so it depends on temperature only. It only depends on the temperature. So with the temperature, it is going to change. It is going to change with the temperature. Okay. Now, why does it depend on concentration? Because if the concentration of any one of the thing is changed, then the equilibrium reshapes itself and attains a new state where Kc is going to have the same value. Kc is going to maintain that value of Kc. The equilibrium is reshifted, and the shift of equilibrium is given by one very important process, one very important theory, which is with the law called as Le-Chatelier's law. Le-Chatelier's law says that the shift of the equilibrium is such that it tries to undo the cause of shifting of the reaction. The cause can be increase in or decrease in the concentration, change in temperature, addition of some noble gases, or it might be with the change in temperatures or change in pressures rather. Okay, so these are all involved with the Le-Chatelier's principle. So because we will carry the Le-Chatelier's principle in the next class, but we need to know that because of the Le-Chatelier's principle, it do not depend on the concentration. Okay, it only depends on temperature. That is important to study. Now, if we study the K value, not with respect to concentration, but with respect to pressure, then it becomes Kp rather than Kc. It becomes Kp. Now, this Kp is pressure of product and reactant upon the reactant raised to the power of the stoichiometric coefficient. This is Kp. Now, see, the formula of Kp is easy, but the problem here lies is how to find the partial pressure. How to find the partial pressure of A, B, C, D. Moles will be given to us. Now, partial pressure is calculated by Dalton's law. What does Dalton's law say? Dalton's law says that the partial pressure of anything is equal to mole fraction of that component into the total pressure. Okay, so we need to apply this every time for this. We have 4 times here. If we have 3 things, 3 times. If we have 5 things, 5 times. And then we have to apply this ratio. Okay, so for example, if I have to find the partial pressure of A, then it will be mole fraction of A into the total pressure. And yes, this total pressure will include A, B, C, D, all gases. It will involve, right? For us to know the relation between Kp and Kc, there is an important relation which says Kp is equals to Kc, RT raised to power delta Mg, like this. It is this relation, which is very important. For this relation, 2-3 things are only important, right? 2 or 3 things are more important. That is, if we are considering Kp, that means it is pressure. If it is pressure, that means we are considering the pressure in atmosphere. So for here, R value we have to use 0.082 strictly. Okay, don't forget this. Next thing, temperature must be in Kelvin. Always, it will be in Kelvin. Okay. Next is about the game of delta Mg. Now this delta Mg is the number of moles of product minus the number of moles of reactant, right? But this should be only for gases. Right? If there is no gas, consider it to be 0. Whether it is product side, whether it is reactant side, or if both of them do not have the gas, consider everything 0. Delta Mg as 0. Right? So delta Ng should be product minus reactant. So from this equation, if you see, the delta Ng should be product C plus B minus reactant B plus A. Like this it should be, if they all are gases. For me, I have considered them as all gases. Right? Okay. Now, if delta Ng over here comes out to be 0, then Kp becomes equal to Kc. If delta Ng is positive, then Kp is greater than Kc. Right? If this becomes negative, Kc is greater than Kp. So what does this say? Kp and Kc can be greater, lesser or equal to each other depending upon delta Ng. Right? Whatever is delta Ng that we will be calculating over here. Right? So these are the values, these are some of the formulas that I'm telling you, some of the thoughts which I have given you. Let us try some questions out of them and let's see whether we are able to apply this thing over the questions or not. Right? Okay, so starting with some questions. I'm writing down, not writing the complete question, but the important things. And that is, they are giving that there is 3 moles of PCl5 in 2 liter glass at room temperature. Dissociate 40% to attain equilibrium. Kc, they want you to calculate Kc. Okay? They want you to calculate the Kc over here. Now let us see. PCl5 they are talking about. We know through inorganic that PCl5 is dissociated when it is heated. It is dissociated into PCl3 and Cl3. This is how it is dissociated. At T is equal to 0 time. At 0 time, they have known that this is 3 moles and they are not dissociated. But at the equilibrium time, they say that this is dissociated. How much it is dissociated is the 40% of which was taken. So, 40% of 3 moles that he was taking, it is dissociated. This comes out to be 1.2. Right? And the concentration, the number of moles which will dissociate will be equal to the number of moles that will be formed. Because 1 mole of it is dissociated to form 1 moles of this and 1 moles of this. So 1.2 moles will form 1.2 moles of this and 1.2 moles of this thing. Right? This will come out to be 1.8. Now these are number of moles, not the concentration. For concentration, we have to divide it by volume. Volume is 2 liter. Volume is 2 liter, it will be 0.9, 6 points again. Now it is easy to calculate Kc and that will be 0.6 product concentration upon reactant concentration. This will be the value of Kc over here. So this will come out to be this 0.4 over here. Right? Okay. Next question. See, the next question is value of Kc for isomerization of butane is 3. Find percentage of isomerization. Find the percentage of isomerization. See, maybe they are saying that butane is converting to isobutane, like this, right? Now, they have not given us any initial concentration. Whenever no initial concentration is given to us, we take the initial concentration as 1. For our simplicity, for us to calculate simply, right? We calculate it as the value as 1 molar. You can take 10, you can take 100, you can take X also, right? But for simplicity, for the simple calculation, take it as 1 molar, we can take, okay, 1 molar, so this will be 0. Whenever the concentration is not given. Here it was given, so we took as 3 only. Okay? Now, at equilibrium, this 1 should be dissociated. Let us take it as X, and X will be formed over here. Right? Now, KCO from here should be X product upon reactant 1 minus X, and this value is given as 3. Now it has become now easy, that is, X is equal to 3 minus 3X, and X is equal to 3 by 4 over here. Right? So that is 75% is dissociated. Other way around, the question comes how much of the butane is left for isomerization, that will be 25%. So just read the question wisely. Okay? Now, these are some basic questions. Let us do some previous year good question. And that is this thing they have given. They are giving 4 moles of argon, a noble gas, with 5 moles of PCl5 in 100-liter flask at 610 Kelvin. They are saying that at equilibrium, pressure is 6 atmosphere, and they are asking us to calculate Kb. Kb they are telling us to calculate. Okay. Now, see, for this type of a question, this is similar. The chemical equation is similar as the first one, that PCl5 is dissociating to PCl3 and chlorine, like this they are saying. Okay. But if you see here, this is not only the PCl5 which is present, argon is also present. Now, argon will not affect the dissociation of PCl5, but argon will, argon will add some volume, add moles to the container, because it is a gas and it is adding the moles to the container. I will not say it will add the volume, because the volume is constant, 100 liters, but it will add some pressure to the container. So the pressure which they are saying 6 atmosphere is the pressure of PCl5, PCl3, chlorine and argon also. Understand this? Right? So they are saying at time is equal to 0, they are giving us 5 moles. This is 0. So at equilibrium, our concept says this should be x and this should be like this. 5 minus x and x. But I need to know x. X I will know through the number of moles. In the question they are saying equilibrium pressure is this. We know equilibrium pressure, we know equilibrium temperature, we know equilibrium volume also. So I can apply P is equal to nRT like this. Okay? So from here I can calculate N. N will be pressure 6 volume 100, R 0.082 I told you, and T temperature is 610 Kelvin. Right? When you calculate this, this will come out to be roughly 12. Okay, but this 12 is the value of total number of moles, gases, which is present in the container at equilibrium. So at equilibrium, what all is present? PCl5 is present, PCl3 is present, chlorine is present, and 4 moles of argon is present. This is the total number of moles. From here, I get the value of x, and x will be 3. Right? X will be 3 over here. X is 3, so this will come out to be 2, this will be 3, and this will be 3 over here. Right? They are asking us the value of Kp. What is Kp? Kp is the pressure of PCl3. Pressure of PCl3 will be mole fraction of PCl3, that will be 3 by 12 into total pressure 6. Then partial pressure of chlorine. Partial pressure of chlorine will be mole fraction of chlorine, again same, and the total pressure. Then partial pressure of PCl5, that will be 2 by 12 into 6. Like this it will be. Right? Now, when you calculate this, now it has become the normal general calculation. And this will come out to be around 2.2 kb. Right? Now, so if you see the question, this question, the basic question only. Right? It is a basic. See, this question, if argon would have not been added, this question would be like this. Right? But this question becomes a little tricky because of addition of some noble gas, where we have to use some other formula which we are already using in the other chapters, in the upcoming chapters. We'll be using it also. Right? So this becomes easy when you apply it, considering the situation a little real, that what they are actually talking about in the question. Right? Okay, so this is how we will apply. There are other concepts also about this chapter that we'll be taking in the other class. Okay, thank you.